Okay. So this triangle is, this angle is 90, this angle is 20. What's this angle going to have to be here? 70. Okay. What kind of angle pair do we have with this angle here? So this angle here has to be 70 because they have to be congruent. This is 25 and that's 70. That's 95. So what's this angle going to be? 85. There we go. Okay, so we got X. Now to get Y. Well, actually, what I'm going to do is I'm going to look at this triangle. So this is also 90. And if this is 25 and this is 90, this is 65. So 65 and 25 and 90 make up the right triangle. So that's the way I do that. You have to kind of pick out which triangles you want to work with. And so it's a little bit puzzle-like, in a way. I mean, we also knew that a couple other things we could have known is that, well, this is 85, this is a linear pair making that 95. This is 70, so this is a linear pair making that 110. And then I could do these three angles, and the fourth angle has to add up to 360, because it's a four-sided one. So I could have done something like that. I get this angle as 110 over here. I don't think I can get these two angles. I just don't have enough to do it. Can't quite get those. But look, I've solved a whole lot of angles. And that's the way these problems work, is you just start, even if you don't find the one you're looking for right away, you find other angles first. You just keep, okay, what do I know? If I can't find the one I'm looking for right away, which one can I figure out? And how does that help me with the next one? How does that help me with the next one? Okay, yes. 19, sure. Back a page. Alright, so you have 3x plus 2x, right angle and angle 1. Something like this. So right angle, this is 3x plus 2, this is x, and this is what we're looking for out here, angle 1. That's what we're looking for. Now, in order to find angle 1, we're going to have to solve for x first. So, looking at my triangle, I know I used up 90 degrees here, so these two angles has to equal what? 90, because they're two acute angles of a right triangle. That's the way that works. So I add those together. That's 4x plus 2 equals 90. So 4x equals 88. So x is 22. So then this angle out here is 180 minus 22, or 158 degrees. Okay? Any other questions? They take a little bit of problem solving sometimes. You got to set up and solve equations. You got to figure out what you know. Again, these are algebra problems where you don't get straight to the answer. You have to work through it one little piece at a time. And then we get to the answer. There were a couple problems that were in the coordinate plane today, and they kind of lead us into where we're going, because we're going to work in the coordinate plane. 11, 12, and 13. 11 gave us 3 points, 2, 3, 6, 3, and 2, 7. So it gave us 3 points, 2, 3. Hard to see the squares here sometimes. I'm not close. Okay, 2, 3, 6, 3, and 2, 7. And they ask, what kind of triangle does that form? And that's not too tough of a question, because it's pretty easy to figure out that this is a right angle because you have a vertical and a horizontal side. So that is a right triangle, correct? And it's pretty easy to find the lengths of these two sides because 1, 2, 3, 4, we can just count boxes there. And this is 1, 2, 3, 4 also. So that is a right isosceles triangle. We don't have to worry about it being equilateral or anything, do we? Because it's a right angle. Equilateral triangles are always equiangular, which means they can't have a right angle. Right? Understand? Correct? Does that make sense? If I know it's a right triangle, it can't be equilateral. Equilateral triangles are never right. They're always 60, 60, 60. Equiangular. So I can put things in the coordinate plane and decide what's going on. Now, what would we have to do to find the length of this side if we did need to know it? How could I find the length of that side? What formula do we use to find the length in the coordinate plane? Distance formula. So all I'd have to do is set up a distance formula with those points, 2, 7, and 6, 8. So 6 and 2, 3 and 7. It's the square root of 4 squared plus negative 4 squared. 16 plus 16, the square root of 32, which is the square root of 16 times the square root of 2, or 4 root 2, is the length of this side. So I'm able to find the exact length of that side using the Pythagorean theorem, if we need it. Working in the coordinate plane is what we're looking at today. And we're going to be working with proving that triangles are congruent in the coordinate plane. Now, there's only so much we can do at this point in the coordinate plane. We can't necessarily measure angles. We can only pretty much measure sides. We can see if something's perpendicular by finding the slopes, if it's a right triangle or not. But really what we're going to be concerned about is proving triangles congruent, which means looking for congruent sides. And the only way we can find congruent sides is by using the distance formula. So what it's going to mean is if I'm trying to prove two triangles are congruent, I'm going to have to find the lengths of all their corresponding sides, which might mean doing 6 distance formulas for one problem in a lot of cases. This is kind of like what we did last night. Let's see this again. Just kind of reviewing. Classify the triangle based on what we see here. Again, I'm sorry it's kind of washed out. I don't know why it's so washed out with the projector, but it is. The points are 2, 1, 5, 3, and 3, negative 3. 2, negative 1, 2, negative 1, right there. 5, 3, and 3, negative 3. The question is, what type of a triangle is that? Okay. It would appear to be scalene and obtuse. But how could I prove that it's scalene and obtuse? Yeah. Find what? Are on? You think something's wrong here? Did I put a point in the wrong plot spot? Okay, yeah.
I have a question.
Yeah.
How do you, how do you know it's not acute because there's 2 acute ones in there?
Well, how do we measure? We always go by the largest angle.
Okay.
The largest angle is how we classify. All right. So, back to where we were. How can I prove I can't necessarily prove obtuse. I can prove that it's not right by finding the slopes of the sides and showing that no sides are perpendicular. If I can't prove that it's obtuse, we need trig for that. We'll find a way later this year we could actually do that, but not for now. Actually, once we get Pythagorean theorem, once we get all three sides, there's a way of proving that it's obtuse, but that's in the right triangle chapter. We can't do that yet. But we can prove that it's scalene. And the way that we prove it's scalene is by finding the length of each side. So this is A, this is B, and this is C. So what we do, and this is the kind of work that you're going to be doing tonight, is you're going to be using distance formula to find the lengths of sides of triangles. And it's going to be a lot of drill and practice on the idea of distance formula. You're going to do a lot of distance formulas. Make sure you label what you're finding. AB equals, start with A and B. 5 minus 3 squared, or 2 minus 5 squared. Negative 1 minus 3 squared. So square root of negative 3 squared plus negative 4 squared. 9 plus 16. That's the square root of 25, which is 5. So I just found that this side is 5. Let's find AC. And again, we label it. 2 minus 3 squared plus negative 1 minus negative 3 squared. So plus 3, 2 minus 3, that's negative 1 squared plus 2 squared. 1 plus 4 is the square root of 5. That's the length of that side. So far, no two sides are the same. I have one that's 5, one's the square root of 5. Now I find the third side, BC, and we show our work. Again, 5 minus 3 squared, 3 minus negative 3 squared. So 3 plus 3 squared. Square root of 2 squared plus 6 squared. 4 plus 36, that's the square root of 40. I'm not going to bother simplifying that because I can see that all three are different, aren't they? Simplifying isn't quite as important here, but what is important is that we find the correct length of all three sides. And then I can very definitively say with full confidence that that is a scalene triangle because all three sides have different lengths. And that's using the distance formula to do so. The other thing we can do is say, well, let's see if triangles are congruent or not. These are three triangles that are congruent, two triangles. Are they or are they not congruent? The only way I can do it is by using distance formula to measure the lengths of all the sides. Now, if a side is vertical or horizontal, like here, NT is horizontal, I do not need to use distance formula. I can just count boxes, right? It's horizontal. So it's 1, 2, 3, 4. This side is 4 units long. This one is vertical, 1, 2, 3, 4. This side is 4 units long. So we got those sides ready. I don't need to show calculation for that. Vertical and horizontal ones are freebies. You do not need to show calculations on vertical and horizontal sides. All right? You guys want to keep your heads up and pay attention, folks. Otherwise, you might wind up doing more than you need to. So for vertical and horizontal segments, we do not use distance formula. For other segments, we must use distance formula. And that means finding the coordinates of the points. This one is R is at 1, 2, 3, 4, 5, 6, 7. This is 1, 7, 8, 9, 10, 11. This is 1, 11. This is 2, 3, 4, 5, 10. N is at 1, 2, 3, 4, 1. This is at 8, 1. And this is at 7, 1, 2, 3, 4, 5, 7, 5. All right, so we found the coordinates of our points. Now we start finding the lengths of sides. And when we find lengths of sides, we label what it is we're finding. I already know CR and NT. Let's try CA. And we set it up. 1 minus 5 squared 11 minus 10 squared. Oops. Simplifying 1 minus 5, that's negative 4 squared plus 1 squared. 16 plus 1, that's the square root of 17 is this side. That's fine. Which side do I think that's congruent to? I think that's congruent to IT. So maybe over here I'll calculate IT and show my work again. 8 minus 7 squared, 11 minus 5 squared. I'm sorry, 1 minus 5 squared, not 11. I knew something was off there. Square root of 1 squared plus negative 4 squared. Square root of 1 plus 16, square root of 17. Aha! These sides are congruent, aren't they? They have the same length. So now I've proven that two pairs of sides are congruent. I have to do it for the third pair of sides. It takes a bit of patience. Third side is AR. So it would be 1 minus 5 squared. Notice I always label what it is I'm finding. And 7 minus 10 squared. Square root of negative 4 squared plus negative 3 squared. So square root of 16 plus 9, that's 5. Square root of 25, that's 5. Then we find NI. Same thing. 4 minus 7 squared. 1 minus 5 squared. It's the square root of negative 3 squared plus negative 4 squared. Square root of 9 plus 16, excuse me, is 5. Square root of 25, which is 5. So this is also 5. So all three pairs of sides are congruent. That proves they're congruent triangles. That's what it takes to do these problems. What this assignment comes down to is repetition with distance formula. Lots and lots and lots of repetition with distance formula. Not so much slopes or midpoints yet. We will get to those in coordinate proof in time. For now, it's primarily distance formula. And when you look at just these few problems that are assigned, it's not a big assignment. Not at all a big assignment. It's 9 through 12, 21, and 22. So 237, 9 through 12. They give you the points in the coordinate plane. You're probably best off drawing the picture and then showing your work. You must show your work on this homework, okay? You can't just say, yes, they're congruent, no, they're not congruent. If you don't have the distance formulas down, if you don't show me every distance formula calculation, they aren't congruent. You're not done. You must show your work. Drawing the picture helps you determine what vertical and horizontal lines there are. Those you don't have to show work for. So that's what you're doing very specifically in 9 through 12. The other page was 260. '21 and 22. And again, it's the same thing. The exact same thing. It's a different page. You're doing the same thing. You're just working in the coordinate plane. So you have 6 problems. Each one will have 6 distance formulas at most. So that's 36 distance formulas. Is basically what today's homework is. Lots and lots and lots of repetition on distance formula tonight. But it's about the only thing you do. So, if you need graph paper, which I'm going to have a big need for this year, but do I have some leftover graph paper here from last year? Maybe. Maybe not. I thought I did, but apparently I do not. Well, the easiest thing to do then is to go get some. You know where we go get some? www.mathbits.com. Free downloadable graph paper. Oh, looky what I found. Oh, one page is 4 4x7s, 7x7s. Okay. Let's see that. I'm going to print 2 of them, and then I will actually go and make some back-to-back copies in the copy machine for you. Okay? And you can take as much of this as you only need 1 sheet for today. But you'll need extra space to show your work. So realize the drawing is not your work. You actually have to show your distance formulas. Am I going to give you credit if you aren't showing all your distance formulas? No. The only ones you can't show distance formulas for are, or you don't need to, are horizontal and vertical lines.